Next slide. To find a planet's mass, we use satellites and Kepler's third law, Newton's version of the third law. In the telescope at closest approach of Mars, we see that Mars's closest moon, Phobos' orbit, has an angular size of 35.3 arcseconds across and an orbit period of 7.65 hours. For the orbit size, we need a real physical distance, as in how many kilometers or miles it is from the center of Mars to the center of Phobos. In order to convert the 35.3 arcsecond angular size to a physical distance, that requires we know the distance to Mars. We find that Phobos' orbit size is 9,400 kilometers, and when we plug that into Newton's form of Kepler's third law, we find that Mars's mass is 6.4 times 10 to the 20th metric tons, or about 10% that of the Earth. Click the image to bring up another animation comparing the motions of moons going around two planets. Satellites moving around a massive planet orbit faster than satellites at the same distance from a low-mass planet. That's illustrated with the blue moons, which have the same orbit size. Other stats for the moon orbits are given below, and notice that the red moon's orbit is twice as big as the blue moon's orbit, but its orbit period is more than twice as long, as given by Kepler's third law. In Newton's second law of motion, the force applied equals mass times the acceleration. So the amount of acceleration something experiences equals the force applied divided by the mass of the object. Greater force makes greater acceleration, so the satellite's orbital velocity is greater and the orbit period or time is smaller. In this case, of course, the force is gravity. So to make a greater gravity force, you either increase the mass of the central primary body or you make the orbit smaller. If Phobos was orbiting the Earth at the same distance of 9,400 kilometers from Earth's center, Phobos would take just 2.5 hours to orbit Earth instead of the 7.65 hours it takes to orbit Mars. Would you make the orbit around the Earth bigger or would you make it smaller? So Phobos' orbit period equals 7.65 hours. To summarize the measurements needed to find the mass, you need either the orbit speed or orbit period and the center-to-center distance between the planet and the satellite. Next slide. To determine the diameter of a planet, the simplest method uses the angular diameter, or angular size, which is how big it appears in terms of an angle. The measurements that are made are the angular size and the distance to the planet. If you use the formula given in the picture, you need to make sure the angular size is in degrees. Since we're dealing with really far away objects, the angular size is going to be a tiny fraction of a degree. Here I go through an example for Mars at its closest approach to Earth. It is just 25.5 arcseconds across, but with a telescope under high magnification and steady air, you can see a bit of details on the surface. The angular size in degrees is just 0.00708 degrees when the distance is 55 million kilometers from Earth. Plugging the numbers into the formula, you find that Mars is 6,800 kilometers in diameter, which is about half Earth's diameter. This technique works if the planet is close enough for us to see a disk instead of just a pinpoint. If the planet is too far away for us to see a disk, then we hope there's a moon orbiting the planet and that its orbit is aligned with our line of sight so that they will eclipse each other. During the eclipse, also called a transit, the overall brightness of the system will drop down. If you know how fast the moon is moving in its orbit, the diameter of the planet will be the moon's speed times the eclipse time. The moon's speed is found from either the Doppler effect or from combining the angular velocity and the planet's distance from us. Before we had the Hubble Space Telescope, we used this eclipse transit technique to find Pluto's diameter was smaller than the moon's. There was a 5-year window when Pluto's largest moon, Charon, was lined up with our line of sight. If we had not discovered Charon in time, we would have had to wait about 125 years for them to be lined up again on the opposite side of Pluto's orbit around the Sun. Once you know the diameter, then how much three-dimensional space it occupies, its volume, is just pi divided by 6 times the diameter to power 3. The power 3 comes from the 3 dimensions of space we live in. Next slide. Putting the mass and volume together, we can get the density, which is an important quantity to determine because it indicates of what the planet is composed. The density is how much material there is in a given amount of space. Mathematically, mass divided by volume. The density depends on the composition of the material. Planets, moons, etc., made of the same material will have the same density. The picture shows things with very different densities but the same mass. The reference material we use is water because it has an easy to remember density of 1. Either 1 gram per cubic centimeter or 1 metric ton, 1,000 kilograms, per cubic meter. Ordinary silicate rock like we have on Earth's surface has a density of 3 times that of water, and iron has a density of 7.8 times that of water. The 4 inner planets in our solar system are terrestrial planets, which means they are rocky worlds like the Earth. Their densities range from 3.9 for Mars to 5.5 for Earth. These are numbers between those for silicate rock and iron, so they must be made of a combination of rock and iron. The higher the density number, the greater proportion of iron there is in the planet's interior. The definition of a terrestrial planet that can be used anywhere in the galaxy is a rock-iron world with a thin atmosphere. The 4 outer planets in our solar system are Jovian planets, which means they are gas-liquid worlds like Jupiter. The Jovians in our solar system have densities ranging between just 0.7 for Saturn on up to just 1.6 for Neptune. Definitely not rock and iron. They are made of much lighter material, and spectroscopy of their atmospheres tells us they are hydrogen, helium, gas, and liquid worlds with thick atmospheres. That definition of a Jovian planet can be used anywhere in the galaxy. Next slide. This slide summarizes the general features of our solar system that any model of its formation is going to have to explain. The orbits are nice and orderly and aligned with the Sun's equator, and they all move in the same direction. The Sun contains most of the mass, but the planets contain about 90% of the solar system's angular momentum. There are 2 types of planets, with the terrestrials in close and the Jovians farther out. There are smaller bodies called asteroids, with most of them in between Mars and Jupiter, and comets that are found in 2 places, the Kuiper Belt and the Oort cloud, that I'll describe in a later lecture. The formation model will also need to explain the exceptions to the general trends, such as the strange spins of Venus and Uranus, and how Earth's moon is so large compared to Earth's size. Also, the very small moons of the planets can have some real unusual orbits, while the larger moons are much more orderly.